Hi, y'all. Welcome back. I'm Nathaniel Woodward, and I'm going to be talking to you today about Two-Way ANOVA. It's really not that big of a leap from One-Way ANOVA, but we have to go talk about interactions for the first time, and it's going to be a fun day. It's one of my favorite topics. Um, cool. Hope you had a nice weekend. I what did I do? I think we made my spouse and I made some sourdough cinnamon rolls for the first time, which was really interesting. It doesn't sound like it'd be good, but it was really something about the tanginess really uh, does something interesting to the sweetness. Uh, what else did I do? Oh, if you're a Fiona Apple fan, I'm sure you already know uh, her album dropped a couple days ago on Friday, like a month after she announced it, which is, I mean, people knew it was coming, right? But I've been listening to that thing nonstop. It's brilliant if you're into her. If you haven't listened to her music before, it's like, how do you describe it? Sort of like classical lounge punk. It's very unique. It's its own thing. Um, Brilliant album. Super stoked for it. Uh, but anyway, I don't want to. This is going to probably be a long lecture because we're going to need to review the one-way ANOVA concepts, and I've got some extra practice problems too. And I just want to do make sure that the coverage is pretty thorough because the book doesn't do a great job of talking about interactions and especially with respect to two-way ANOVA. Cool. So let's get moving. So that's what I said, right? Two-way ANOVA. First, we got a review. Um, you can't see this stuff enough, right? The more you review it, the better it sinks in, and that's especially true for making the segue from one way to two-way ANOVA. So after we review one way ANOVA, uh, we're just going to start kind of broad, like zoom out a lot and look at the forest instead of the trees and be like, hey, what is a two-way ANOVA? How do we think about a two-way ANOVA conceptually before we dive into like, running it and interpreting it? Um, and in so doing, we're going to talk about interactions. Interactions are really cool. Kind of as a spoiler, they're nothing mysterious. It just means that the effect of one variable on your response depends on the other variable, right? So, like, maybe you've got a new uh, drug to try to treat, I don't know, high blood pressure, right? Maybe that drug works, but it works really well for elderly individuals and it works substantially less well for younger individuals. So that would be an interaction, right? That would be an age by drug interaction. So we'll talk all about these kinds of things as we go forward. Um, cool. And then of course we have to do a full example so you can you know uh, actually do the homework and the labs and stuff correctly. So that'll be there too. Uh, cool. And as I said, I'll post a couple extra practice problems at the end just for fun. Um, So you've got a quiz coming up, and you might not even watch this video until after the quiz, although I'm going to encourage you to watch it before the quiz, because we do review ANOVA, and the more times you go through this, the quicker you're going to be able to do it, and just the easier it's gonna be for you. It'll really start to sink in. But like anything, right? Practice makes perfect. Uh, cool. Now I'm not sure. I don't think you've seen this. I toyed with whether or not we should spend the time looking at this, but it's a really cool app that our department developed, and you can make these apps in R. So take a look at this. You can follow this link if you want. It's going to be active in the slides. It's utsds.shinyapps.io / ANOVA V variants. And if you follow this link, you end up right here. See, just that URL. Cool. So check this out, right? It's a typical ANOVA situation. It's kind of flipped on its head because we've got the response variable down here, and then you've got your three groups, right? And in this case, the diamonds are representing the means for each group. And in this case, they're all equal, right? Each group has a mean of 100, 100, 100, 100, and you can see them all lining up, right? Um, Remember with ANOVA, it's all about comparing group means in the population. So you might be interested to know whether uh, groups 1, 2, and 3 in the population all have the same mean, right? And we get a sample of each. In this case, the sample size is what? I think how big is the sample size? I think it's 25 each. Yeah, the sample size is set at 25 each. So you have groups of size 25, right? And the means aren't different from each other. They're all equal to 100, right? Think back to last time in the ANOVA example, right, where the between group sum of squares, you're comparing how different the groups are when you compare their means. And in this case, their means are all the same. They're all 100, right? So when you compute the between group sum of squares, it's 0. There's no difference, right? When you calculate how far one group's mean is from the grand mean, another group's mean from the grand mean, another group's mean from the grand mean. Well, the grand mean has to be 100 too, because all the group means are 100, right? So there's no difference. So there's no differences between groups here. And that's being reflected in this group or between group sum of squares, right? It's 0. The error sum of squares is a function of how much noise there is within each group, right? And we can crank up that noise. We can, you can watch and see how the error sum of squares gets bigger and bigger as the groups get more noisy, right? As the individual observations within each group get more spread out on average from their own group mean. It doesn't change the between group sum of squares, right? You still have a 0 F statistic, right? But let's leave this at, I don't know. I think it was set at 15. That's fine. What happens if you, move a group mean up to like, let's do let's move it up, I don't know, let's do 110, whatever. So notice, all we did is we scooted group 1 up to 110. And that doesn't look like a huge difference, right? We can ask, hey, do we have enough evidence here to suggest that there's some difference in means between groups 1, 2, and 3? And so now if you look, the between group sum of squares, now there is a difference, right? Because we have group 1 being different from groups 2 and 3, right? And so notice what happens. Remember before, the F was 0 when there was no difference, and the p-value was effectively 1, right? Well, now we do have differences between groups, right? So your F statistic goes up. In general, right, test statistics that are bigger in magnitude are better. They're more unusual under the null hypothesis of no difference, right? So in this case, it's bigger. And is it significantly bigger? Yeah, that p-value went down, right, quite a bit. So cool. So we know now, this ANOVA is telling us, right, that at least one group is different. And obviously we know which one it is because we twiddled it, right? We know that group 1 is different from 2 and from 3. You'd have to do post hoc tests, right, to know that in any other situation. But watch what happens if we crank up the error, right? So if we crank up the what I typically call sum of squares within groups, but it's the same thing, right? It's just the error. If we crank this up to like 20, watch what happens. These groups got more spread out, right? And that spread caused there to be a bigger within group sum of squares, right? Which leads to a bigger mean square error, or a bigger within groups, like mean square within. That's the denominator of your F statistic, right? So if that thing gets big, your F's going to get small. So now our F statistic is substantially smaller, and it's no longer significant, right? The ratio of the signal, the differences between groups, to the noise, just the variability within each group, has gotten smaller, and that's no good, right? You want the groups to be distinct from each other, and you want there to be very little overlap. We've increased the overlap. That makes our F statistic go down, right? So play with this. It's a really interesting thing to play with. What if we moved group 3? What if we moved its mean down 10? Cool. And hey, look, we kept them spread out, right? We kept the error sum of squares the same, but our between group sum of squares got bigger, right? Because we moved this group down, this group's up, and this group's right in the middle. They're means, right? Just look at those red diamonds. On average, our groups are now more spread out, right? The means are more spread out from each other. And that's reflected in this bigger between sums of squares, bigger F statistic, right? Now the ratio of signal to noise has gotten bigger. There's more signal relative to the noise. And that p-value has gotten smaller, right? So in general, right, the take home here is the more spread out your groups are, the more spread out their means are, with respect to the amount of noise there is, the bigger the F statistic and the smaller the p-value, right? I mean, you can think of something crazy, like if you imagine we had very little error, right? So if we lower this to something very small, now these are much more distinct, right? And that p-value is effectively 0. It's a very, very small probability that you would get groups that are this different if you were sampling from a populations that have the same mean. And that's really all an ANOVA is. Cool. So this is just something fun to play with, right? Like if you want to keep sort of broadening your intuition for these things. But let's do an actual example, because I know this is kind of, it lacks context. It's just talking about groups and outcome or whatever. So let's actually do an example. Feel free to tinker with this, right? Whoops, where did my, no, there it goes, sorry. Cool. So this to me is like the picture of a one-way ANOVA. Like this captures everything about a one-way ANOVA. You've got some response variable, right? And in this example, sort of spoiler, we're going to do this example later. This is guinea pig tooth growth. And you're looking at how much guinea pig's teeth grow over time. And you're giving them different dosages of vitamin C. So a low dose, a middle dose, and a high dose, right? The actual numbers are like 0.5 milligrams, 1 milligram, and 2 milligrams. This plot over here is illustrating the total sum of squares, right? How far is each guinea pig's specific tooth growth from the overall average tooth growth for all guinea pigs, right? That's that black line. How far is it? That's just these individual vertical black lines from each dot to the grand mean. The grand mean, when I say grand mean, it's just the overall mean. Like if you took the average of guinea pig tooth growth, or whatever your response variable is, across all individuals, that's just your grand mean, right? So if you see how far each data point is from the grand mean, you take that difference, you square it, and you add them up for all the guinea pigs. That gives you the total sum of squares, or the total variation in the response variable. And that's really all it is. If you remember how to calculate a standard deviation or a variance, you'll notice that this is just the numerator of a variance, right? If you were to calculate the variance of the response variable, that's just the numerator. How far is each guinea pig's individual tooth growth measurement from the average tooth growth measurement across all guinea pigs? Do that for each guinea pig, square them, and add them up. And that's your total sum of squares, or sum of squares total. And then ANOVA takes that, right, and it says, hey, that's the total variability in tooth growth. We can break that down into a piece we can explain by knowing what group the guinea pig was in, and a piece we can't explain, the leftovers, sort of the noise that the model can't account for, right? The noise, let's start with the noise. So if you look over here on the far right-hand side, right, what do you think these colored horizontal bars represent? That one, that one, that one. You can see they're like right in the middle of their cluster, right? Here's the low dose group, here's the middle dose group, here's the high dose group. And you can kind of see, yeah, the high dose group tends to have greater tooth growth on average. The middle dose group has middling tooth growth on average, and the low dose group has low tooth growth on average, right? Yeah, so those horizontal bars are just the mean for each group. Those are your group means. Cool. To calculate the sum of squares within, or the sum of squares error, this is just the noise, right? This is the scatter of the points around their own group mean. Like once we know the group mean, this is what's left over, what we can't explain. So it's very similar to sum of squares total, except for instead of taking the difference between each data point's tooth growth and the overall average tooth growth, you take the difference between each data point's tooth growth and the mean for its groups. So this blue bar is the mean for the high group's tooth growth. So you see how far each individual is from that mean, square it and add it up. Do the same thing for the middle group. How far is each guinea pig's individual tooth growth in the middle group from its middle group mean, square those and add those up, and do the same thing for the low group, right? Cool, so that's the noise. That's the stuff we can't account for just by knowing the group means. If you know what group a guinea pig's in, that allows you to make better predictions than if you didn't, right? If you didn't know what group a guinea pig was in, your best guess would be the overall mean. You'd have nothing else to go off of, right? But if you knew what group a guinea pig was in, you'd be making better predictions, right? You'd be able to say, well, I know that guinea pig is in the low dose group, and on average, the low dose group got around, whatever this is, 11. So I'd predict 11, and I'd be much more correct on average than I would be if I predicted 20, which, or 19 or whatever this is, the overall mean. That brings us to sum of squares between. How much of the total variability can we explain by knowing what group a guinea pig is in? So cool. So again, we have these horizontal colored bars. Those are still your group means. But now you're asking, hey, how spread out are my group means from the grand mean on average? So in the low dose group, you just say, hey, how far is the low dose mean from the overall mean, that black line, right? And you do this, you have to multiply it by the number of individuals in that group, right? And that's illustrated by all these little lines, right? We've just multiplied it by the number of individuals in that group. We have to weight it so it's fair to compare. So how far is this bar from this black bar? Take that and do it as many times as there are individuals in this particular group, square them and add them up. Do the same thing for the middle group. How far is the middle group's average tooth length from the overall average tooth length? Weight it by the number of individuals in the group, square them, add them up, and do the same thing for the sum of squares for the high group. The high dose group, how far is the high dose mean from the black bar? How far is the blue bar from the black bar? The group mean for high dose compared to the grand mean. Square it, add them up, and then weight it by the number of individuals. And you can compute these, right? So I'll introduce this notation in more detail later, but this just represents the grand mean, right? And this will be the mean for group K, whatever group that is, if K is low or middle or high. And that'll just be the number of individuals in group K. And again, that's still the grand mean. And this YIK is each individual guinea pig. How far is each individual guinea pig from its own group mean squared and added up, right? And again, you won't have to do the sum of squares calculations by hand, but personally, I didn't feel like I understood ANOVA very well until I saw, okay, how do we break this total variation down into the part we can explain by knowing what group a guinea pig is in, and then the leftovers, the part we can't explain. Cool. So if you were to run this, right, if you were to actually conduct this test, you'd say, hey, the null hypothesis is that the true mean tooth length for guinea pigs in the low dose group, the middle dose group, and the high dose group is equal, right? Which is to say dose has no effect on average tooth growth in the population. The alternative, of course, is that at least one of those is different from the others. And ANOVA just tells you it's testing whether or not there is a significant difference between at least, one of your groups and one other. You don't know which until you do post hoc tests. It just gives you that overall test. Are any of my groups different? Which is a really handy thing to know a lot of the time, right? Cool. So if you were to write out this null hypothesis in words, all you're saying is the true mean of the response variable, in this case it's tooth growth, but whatever it is, the true mean of my response variable is the same for all three groups, or ever how many groups you have, in this case low, middle, and high. In order to test that null hypothesis, we need to compute an F statistic, and then we need to look and see what the distribution of that statistic is if this were true, if the null hypothesis were actually true and there was no difference. If our F statistic looks really weird in that distribution, we can reject that null hypothesis. That's not an accurate picture of the world, right? It disagrees with what our data are telling us. Cool. And that F statistic, again, is just a ratio of the variability you can explain, right? So the mean square between groups to the variability you can't explain, or the noise, the mean square within groups, or the mean square error. Cool. And these are all just things that appear in your ANOVA table, right? You won't have to do them, you'll have to do this by hand, but you won't have to calculate those sum of square things by hand. I just think it's really useful to be able to see it. So as we saw, right, if this F statistic is large, it means that mean square between is large relative to the mean square within. That means your groups are more spread out with respect to each other relative to the noise, right? So they'll be more spread out and they'll have not a whole lot of noise in each group. If your groups are super noisy, they need to be a lot more spread out for this to be significant, right? If your groups don't have that much noise, then the differences in means can be smaller, right? Either way, that's just the difference between making the numerator bigger, right? If you make the numerator bigger, F gets bigger. So if you're making the signal bigger, right, how spread out the groups are, F will get bigger. If you make the denominator smaller, right, if you decrease the noise in each group, that also makes F get bigger. So these two things are sort of working together. If you have a small F statistic, right, that means there's not a lot of not a lot of differences between groups. And or you have a bunch of noise and you just can't really tell whether the groups are different. That's all an ANOVA is doing. It's comparing, hey, how much of the variability can we attribute to differences between groups and how much of it is noise? And you can condense that into this single statistic, this F ratio. Cool, so assumptions, right? So just to review these from last time, as always, you have to have a random sample. The observations need to be independent. The groups also need to be independent, right? There needs to be no way for a guinea pig to be in, the low dose group and the high dose group. The groups should be independent of each other as well. And usually these things will be true, right? Oftentimes we just, we assume these are true for in-class examples. You also have the normal distribution assumption and the homoscedasticity assumption. So there's lots of ways to assess these, right? And different professors have different ways that they want you to assess them. I really don't care. I'm going to show you different ways and hopefully cover the gamut of ways that you might have encountered. An easy way to do the normal distribution is to just make histogram or box plot or QQ plots of the response variable in each group, right? So in this case we had 3 groups. We could look at 3 box plots of the response variable and see if they're roughly mound-shaped, symmetrical. And you could also just so we'll talk later about making a plot of the residuals, which is really just the errors, right? The how far is each observation from its own group mean. If you take all of those and make a histogram or a QQ plot or a box plot, that's effectively doing the same thing. So we'll see that as well. And then Professor Blondo introduced you to the Shapiro-Wilk test. You can also run that on the residuals if you don't like eyeballing plots. And that'll tell you, it'll allow you to test the null hypothesis that the errors are normally distributed, which is what you want to be able to do. We'll see all of these in practice, right? So normality, right? It's important. If you have a big enough sample size in each group, it's much less important, but it's a good idea to eyeball to make sure nothing wacky is going on. You also have an equal variance assumption, or a homoscedasticity assumption. Some people call it homogeneity of variance. It's just saying, hey, in our 3 groups, do their spreads look similar, right? Because we're making the assumption that, maybe like low dose, high dose, middle dose, in the population, we're assuming they all have the same spread, the same standard deviation. All we get is a sample. So we look at our sample and we say, hey, do the samples look like they could have come from a population that has the same standard deviation? And all you're looking for is one to have a wildly different standard deviation than another one. You can just eyeball box plots for this, right? If they have a pretty similar, IQR, like if they look pretty comparably spread out, chances are things are fine. When I was first taking intro stats, though, I was really annoyed at eyeballing plots. It's like, why? Just give me a hard and fast test that I can do and just be done with these assumptions. So if you don't like eyeballing plots, we'll talk about using Levine's test. We've already talked about using Levine's test, right? You can do it for two-way ANOVAs too. And that just tests the null hypothesis that the population standard deviations are equal in each group. So you don't want to reject that, right? Or you've rejected the assumption of homoscedasticity. You can also you can use a rule of thumb that says the standard deviation in one group shouldn't be twice as big as the standard deviation in another group. There's a bunch of rules of thumb, right? Any of those will be fine. Levine's test is probably the easiest to run, and it's just, it gives you a nice hypothesis test that lets you, just move on with your life. So that's however you want to do it. Whatever your professor prefers is do that, right? Cool. This thing. So you'll notice these come up again and again. We have to make lots of assumptions, and they're usually about either normality or equal variances or homogeneity of variance, or having a sample size that's big enough or something like that. think about it, right? Any assumption we made, like the chi-squared assumptions, they're all about sample size. So when we do parametric tests using, actual distributions, and like I know we don't use the tables, but when we do that, we have to make all these assumptions, right? So that's why you keep seeing these again and again. And here's just a schematic of the ANOVA table you're hopefully familiar with right now. The between groups sum of squares, or the signal, if you will, like what's the total variability between the groups themselves? You want that to be big. The within group sum of squares, the noise, you want that to be small. And then the total sum of squares, right? And you can always, these add up. So if you add up between, within, you get the total. Same with degrees of freedom. Here, capital K is just the number of groups. So in our guinea pig example we were talking about, we're doing, what do we got? 3, right? So 3 minus 1 would be 2. Capital N is just the total number of individuals in the sample. We're going to do the full guinea pig example in just a second. But just know that I think it's 60. So here you'd have 60 guinea pigs overall minus 3 groups. So that'd be 57 degrees of freedom there. And then your sum of squares total is just the total sample size minus 1, right? So that'd be 59. And these also add up. 2 plus 57 would give you 59. To get your mean squares, just divide the sum of squares by the degrees of freedom. You get your mean squares. So here's your signal, here's your noise, here's that F ratio, right? Comparing the variability between groups to the variability within groups. You want that to be big, right? If it's not big, womp womp, right? You can't reject the null hypothesis. That the group means are all equal. Okay, so let's actually work through this full example because we're going to use it later when we talk about Two-Way ANOVA, and I want it to be familiar before we get there. So we'll be asking the simple question right now: how is guinea pig tooth growth influenced by vitamin C dosage? And you can run this in R if you want, right? This data set is built into R, and I wanted to do this example because, I wanted you to be able to play along if you're interested in using R. Again, you don't have to do any R stuff on any of the quizzes or anything like that. So don't feel like you have to, I just want to show you that you can try this at home and it'll work. So it's built in, but it treats dose as numeric. So I'm going to go ahead and make dose a factor, right? That's all this is doing. So you can just run these 2 lines of code in R and it'll automatically spit this out, right? And it's just showing you the first few observations. So guinea pig 1 had a tooth growth of, that's the response variable, right, of 4.2, and got the dosage that was 0.5 milligrams of vitamin C. And don't worry about this other variable for now. Guinea pig 2 had a tooth growth that was much bigger and was in that same dosage group, right? So that's just all this is showing. There's guinea pigs who got 0.5, there's guinea pigs who got 1, there's guinea pigs who got 2 milligrams. This is just the data we'll be using. Again, you don't need to do this. I just want you to see it if you're interested. Cool. So go ahead and run that ANOVA like you've seen before. So in R, and again, you don't have to do this, but if you were to do this, the data set's called tooth growth. Just say, hey, we're going to see how guinea pig tooth length differs by dosage group, right? And we'll just do ANOVA fit. You can go ahead and do type equals 3. It's not going to matter for this example. We'll talk about more what that means later. It really only comes into play when you have different group sizes and when you're thinking about interactions and things like that. So don't worry about it for now. Any ANOVA you run on this particular data set will give you this output. Cool. So here's our output, right? And you've got the dose sum of squares. So that's the differences between groups, right? That's your between group sum of squares. And then you have the leftovers, the noise, right? The scatter around each group. And that's your within group sum of squares, right? So sum of squares between on top, sum of squares within. You could add them up to get the total sum of squares, right? Cool. Degrees of freedom, k minus 1, right? So 3 minus 1 is 2. There's 60 guinea pigs, so 60 minus 3 is 57. If you divide this sum of squares by its degrees of freedom, that gives you your mean square between groups. If you divide your within group sum of squares by its degrees of freedom, it gives you your mean square within groups, or mean square error. If you take the ratio of the former to the latter, you end up with a big old F statistic, 67, and a p-value that's vanishingly small, right? That's like effectively zero, which is telling you what? The probability, if the null hypothesis were true, the probability we would get an F statistic that big is almost unheard of, right? It would be very, very, very weird. So chances are the null hypothesis isn't true. Cool, but let's do it more formally than that, right? So what's the critical value? If you were to look it up, you'd get, like 3.15, something like that. Our F statistic was 67.42. Huge, right? So relative to the critical value, it's massive. If we were to look at this F distribution with 2 and 57 degrees of freedom, here's what it looks like. And notice, right, F's can only ever be positive. When you take a ratio of, two numbers that have to be positive, right, because we've summed a bunch of squared deviations, that's positive. When you take the ratio of the mean square between, mean square within, those are both positive quantities, so F can only ever be positive. That's why it's also always going to be right skewed like this. But here's your critical value, right? So any F statistic that's bigger than that is weird if the null hypothesis is true. Pardon me. So where does 67.42 fall? That's our actual F statistic. Well, it'd be way out here, right? The probability of getting something that big if the null hypothesis were true is, would be ridiculous. So we can reject the null hypothesis. Our F statistic's way bigger than our critical value. But we should have tested our assumptions first, right? So let's quickly do a test of assumptions here. You could just make a box plot showing the distribution of tooth length by each dosage, right? And you can see, yeah, these look like they have similar range, similar IQR. It's not too concerning. And this is sort of the eyeball it method, right? If you want to look at plots and say, yeah, these are pretty, when you look at the range and IQR and stuff, they look fine. You could also assess normality that way, right? So grab your residuals and make a histogram of those residuals, right? This is really just the deviations of each individual point from its group mean. You can grab those from the model that you fit just by doing fit $residuals. Or you can just look at this and be like, hey, these look roughly symmetrical. I'm not too worried, right? But eyeballing stuff, it's not super satisfying. And students are always like, I hate looking at these plots. I can't tell if it's, does it meet the assumption? It's right on the cusp. I can't, So if you want hard and fast tests, you can use that Shapiro-Wilk test on your residuals to see if the normality assumption is met. And of course, the null hypothesis is that the sample comes from a normal population. So here we run that, we do the Shapiro test on the residuals, and it's giving you a p-value of 0.1, right? So you can't reject the null hypothesis that the data come from a normally distributed population, which is good. That means you meet the assumption, right? We can do the same thing for homoscedasticity, right? We need to test to make sure that these three groups have the same variance in the population. So you can just use Levene test. So when you run Levene's test, just do Levene test, right? You'll need the CAR package, but hopefully you already loaded it. You can say, hey, guinea pig tooth length by dosage, give it the data. That's one way of doing it. There's a bunch of ways of doing it. But cool, it's saying the p-value, right, the null hypothesis here is that the samples come from populations with equal variance. So we can't reject that null hypothesis, which is good. That means we meet the assumption. We want the samples to come from populations with equal variance, right? We want that to be true. So cool. So basically, when you're using like the p-value method of testing assumptions, the null hypothesis is always that the assumption is met. So it's weird because you don't want p less than 0.05, right? You don't want to reject those null hypotheses. That means you're not meeting your assumption. Cool. So anyway, however you want to do it, eyeball, look at p-values, whatever. They're going to tell you the same thing. Cool. So you can do post hoc tests here, right? So if you were to look to see, you already know that we can reject the null hypothesis. So we know that at least one group is different, right? That's what this overall ANOVA output is telling us. A post hoc test we're going to run to see, hey, which groups are different, right? Is it the low dose different from the high dose? Or is the middle dose different from the high dose? Is the low dose different from the middle dose? you're going to do all those comparisons, right? Or whichever ones you're interested in, typically all of them. For a one-way ANOVA, you'll do all of them. And there's lots of ways to do this. I like to do just Bonferrone's correction, right? So what you're getting here is t-tests comparing, hey, does the mean of the 0.5 milligram, the low dose group, differ from the mean of the middle group, the middle dose group, the 1 milligram? And it'll give you the t-statistic. And don't worry about the sign, it doesn't matter. They're always two-tailed tests. And these are the uncorrected p-values, right? So if you just did a t-test comparing low dose to middle, low dose to high, and middle dose to high, right? Because those are the three possible comparisons here. Those would be the p-values you would get. But remember, right, we're doing multiple tests here, and we want to keep the overall type 1 error rate at 5%. In order to do that, you can either, so there are two ways of thinking about it. You can say, hey, let's just change the criteria for significance, right, to adjust for the fact that we're doing 3 tests. So instead of using p equals 0.05 or p less than 0.05 as our criterion for significance, just divide it by the number of tests you're doing. So just divide 0.05 by 3. If you do that, your adjusted alpha, your adjusted significance level, is 0.0167 roughly, right? And hey, all these p-values are still lower than that. So still, it doesn't matter, right? You can still reject the null hypothesis. All 3 of these groups are different, even after using Bonferrone's correction. Cool. Another way you can sort of eyeball this, instead of dividing your significance level by 3, you could multiply your p-values by 3 and see if they're still going to be less than 0.05. It's doing the same thing. And yeah, if you multiply these by 3, you just get 0.0003, so you'd still reject the null hypothesis. However you want to think about it. This is probably the more common way of thinking about it. Adjust your significance level accordingly, and then compare each of your p-values to this adjusted significance level instead of 0.05. So even with this conservative significance level, everything is still significant, right? So all of our groups differ from each other, all of them. And it's important to, it's important to correct for multiple comparisons, because right, if you don't do this, if you just use the regular old p-values from the t-tests, the overall probability that you're making at least one type 1 error is 1 minus the probability that you're not making any type 1 errors, right? And the probability you're not making any type 1 errors for all 3 tests is 0.95 cubed, right? 0.95 times 0.95 times 0.95. 1 minus that is the probability of at least one type 1 error. And that's almost 15%, right? That's no good. So to adjust for that, we have to correct. Otherwise, you're capitalizing on chance, right? You're kind of cheating, right? You want to be able to say, hey, I want there to be a 5% chance that my conclusions are wrong. And that's what an alpha level of 0.05 means. In order to do that, you have to do this adjustment. Otherwise, you actually have close to, it's like a 14.3% chance that you're making a type 1 error, right? So anyway, cool. Always adjust for multiple comparisons during post hoc testing. Cool. Effect size, right? So rounding things out, we haven't written up the full conclusion yet. We still want a measure of effect size, right? So how much of the variability in tooth growth can be attributed to differences in vitamin C dosage? Well, to do that, right, you're asking how much of the total variability in tooth growth is due to differences between groups. So you know what the total variability is, right? The sum of squares total. And you already have a number that represents the variability due to differences between groups, right? The sum of squares between groups. So just take the sum of squares between groups out of the total sum of squares, right? That gives you the proportion of the total variability you can attribute to differences between groups. And this is identical to an R squared in a regression situation. But you might hear it called eta squared, and that's just the Greek letter eta, right? Lowercase. And in ANOVA, for whatever reason, people like to call it eta squared. But R squared is the same thing, right? Cool. So we can compute that, right? We can go back and get, hey, what was our sum of squares between groups? Where is that? Way back here, right? sum of squares between groups, 2426.4, out of the total, which will be like 3,400 and, what is that? 52.2 or something. You got to add them up. Yeah, 3,452.2 is your total sum of squares. So out of the total, how much is due to differences between groups? About 70%, 70.3%, which is actually pretty good. Looks like vitamin C is really explaining a lot of the differences between in tooth growth between guinea pigs. Sweet. Here's a big write-up, and this is, it's good to do a write-up like this. This is sort of the, it's the way you see it done, and it has all the crucial elements. So, talk about the kind of test you did. We did a one-way ANOVA. It led us to reject the null hypothesis and conclude that mean tooth growth differs by vitamin C dosage. Our F statistic was bigger than the critical value, right? There's the F statistic. There's the critical value. You can include the p-value if you want. A large effect was found. 70.3% of the variation in tooth growth could be accounted for by dosage differences. Then you could talk about your post hoc tests, right? So we had an overall significant ANOVA. So which groups were different? Well, we did post hoc tests, t-tests with the Bonferroni adjustment, and you could talk about your adjusted significance level if you want. And it showed us that all the groups were significantly different, right? And you can go back and look at the t-statistics for each comparison and say, like, guinea pigs receiving a dosage of 2 had a greater mean than those receiving a dosage of 0.5. Big t-statistic, small p-value. Dosage of 2 had a greater mean tooth growth than those receiving a dosage of 1. Big t-statistic, small p-value. And, right, finally comparing 1 to 0.5, or comparing middle to low, also big t statistic, small p-value. Cool, and that's really all there is to it. It's a bit of a long write-up, but it's good. It's good practice to do this. You won't. It'll depend on the situation, but this will be kind of the way you'd want to think about it for, doing a full write-up, like for the homework or something, if you were doing post hoc tests or whatever. Cool. So that's all one-way ANOVA review. So hopefully that was, not too wacky, and you felt somewhat comfortable with that. So two-way ANOVA. Again, it's the same idea. We're still going to be looking at means in different groups and how spread out they are from each other. Problem is, we've got more than one grouping variable now, right? So maybe you wanted to look at, let's say you did an ANOVA looking at whether or not the treatment, maybe you had treatment, maybe you had low, middle, and high dose, right? And maybe you wanted to see how that was affecting a patient's recovery rate or something. But maybe you want to look at the effect of age on recovery rate simultaneously and say, hey, does my drug have the same effect at every age group? Or something like that, right? The only way you can do that is by doing a two-way ANOVA or a multiple regression with interactions, which we'll see next week. So this is cool, right? It allows us to simultaneously test the effects of two categorical explanatory variables. So for your project, if you have two categorical explanatory variables, you're doing a two-way ANOVA. So pay attention. It's good. It's a really cool technique, and it really it builds a lot of good habits for thinking about things in statistics generally, especially interactions. Cool. So it'll allow you to test, hey, what's the effect of my drug controlling for age, things like that. And it'll also let you test the interaction, whether it's a significant interaction. Does my drug's effect significantly differ depending on what age group a person is? That's important stuff to know, right? Sometimes it can look like the drug doesn't work at all, but then when you look at, older people, it might work really well, and younger people, it might work negatively, right? It might have a negative effect. Overall, it would look like nothing was going on, right? But if you look at the separate subgroups, you'll see differences. So you wouldn't be able to see that if you didn't fit a model that had the interaction. So we'll see that in just a second. Interactions are so cool, but they take a bit of getting used to. So for each factor, right, and when I say factor, I just mean grouping variable, like dosage or age or, whatever. whatever your categorical variable is, those are just factors. And each one of those and each interaction is going to have its own set of hypotheses. They're going to have their own f-statistics, and of course, they're going to have their own p-values. So you'll be running, like in this example, if you have factor A, factor B, and the interaction, that's 3 hypothesis tests. And that's the way two-way ANOVAs work. Cool. And like we were talking about, right? So we'll spend a lot of time with interactions today, but it's just looking to see whether the effect of one factor on the response variable depends on the other factor or differs depending on the level of the other factor. I know that's very vague and sort of abstract, but we'll nail it down here in a sec. So some assumptions, right? They're effectively the same as the one-way ANOVA, right? You're still dealing with random sample independent observations. You're still dealing with normality, except for each group within each factor should be roughly normal, right? So you have 2 factors, each with their own separate groups, right? Maybe you have dosage, low, medium, high, age, younger, older. Within each of those groups, the response should be roughly normal. And within each of those groups, within each of those groups, the response variable should have roughly equal variance as well. If you were going to assess the normality, you could look at box plots or histograms or QQ plots, just look at the distribution for each group of each factor. Or, much more simply, in my opinion, just make a histogram or something of your model's residuals. So we'll talk about that. You really only need one single plot to assess normality. That's the way that I like to do it. But you could do it by making box plots for each of your categorical variables. That's fine. To assess equal variances or homoscedasticity, you can use Levene's test, or you can just eyeball some box plots, or you could look at the standard deviations in each group within each factor if you wanted. However you want to do, that's fine. I think Levene's test is easier, but whatever. It really doesn't matter. Cool. So how do we think about this? So in a one-way ANOVA, right, we're taking that total variability of our response variable and breaking it into the part we can explain by knowing what group an individual is in and the part we can't explain. So the between groups sum of squares and the within groups sum of squares, right? We're partitioning that total variability into the good stuff and the bad stuff, you could think of it as. The signal and the noise. With a two-way ANOVA, if you fit the full thing, right, with the interaction, you're going to have an effect of factor A. So how much can you explain with factor A? Say it's dosage. You'll have an effect of factor B. Say it's, age. Then you'll have the A by B interaction. How much does the interaction account for? And then you'll have the error, or the within groups, or the leftover sum of squares, right? So the sum of squares error in a two-way ANOVA is completely analogous to the sum of squares within in a one-way ANOVA. It's just the noise that's left over. Once you've accounted for factor A, factor B, and the interaction, how much of it is just junk that we can't explain? Cool. Yeah, so I think I talked about that stuff. You can imagine, right? So when you look at your ANOVA table for a one-way ANOVA, it tells you the sum of squares between groups, the first thing, and then the second thing with the sum of squares within groups, or the error, right? Now we're going to have 4 different lines. Sum of squares for factor A, for factor B, for the interaction, and for the error term. And you can add all these back up, right? When you add these back up, this is just a different way of slicing up that total variability. If you add these back together, you get the sum of squares total, just like the sum of squares within plus the sum of squares between gives you the sum of squares total, right? Cool. And this is important, right? If you know any 4 of these, you can always solve for the last one, right? So if you know, if you know the total, the A, the B, and the A by B, then you can do the total minus this one, this one, this one, and get the error, right? So, you could, it's just an equation. If you have one unknown, you can solve for it, right? Cool. So take a minute and look at this thing. This is a big schematic of an ANOVA table, two-way ANOVA, right? So you'll have an effective factor A with a sum of squares, an effective factor B, sum of squares. The interaction effect, it has a sum of squares. There's your error, or the within sum of squares. And then all these added up give you the total, right? The degrees of freedom, just like in a regular one-way ANOVA, are also additive. So here, little a and little b, I'm letting those represent the number of groups for that factor. So for example, if factor A is dosage and there's high, middle, low dose, that'd just be 3. So it's 3 minus 1. For B, maybe that's age, young, old. So there's just 2, so that'd be 2 minus 1, right? The interaction sum of squares is just the sum of squares for factor A times the sum of squares for, sum of squares. The interaction degrees of freedom, is just the degrees of freedom for factor A times the degrees of freedom for factor B, right? So you can find all these things. This is just the total number of people in your study, total number of observations, minus the number of groups of factor A and the number of groups of factor B. And then this is just the total number of people minus 1, right? Oops, it's weird. Cool, but now look, so we've still got this sum of squares error, which gives us a mean square error, right? Divide the sum of squares by its degrees of freedom to get your mean square. So you get a mean square error, you get a mean square for the interaction, just the sum of squares divided by the degrees of freedom. You get a mean square for factor B, you get a mean square for factor A. Crazy, right? Bunch of stuff going on. This all is boiling down to 3 hypothesis tests, right? We're testing the effect of factor A, the effect of factor B, and the A by B interaction. So these F ratios, you have the mean square for factor A compared to the error, right? You have the mean square for factor B compared to the error, and then you have the mean square for the interaction compared to the error. So notice, the denominator is the same every time, right? It's still this error mean square. The noise is the same for all these F ratios. The only thing that changes is the numerator, the mean square for each of the specific effects you're testing. Cool. I'm not sure what I mean by this here. Ignore that. That's ended up in the slides weirdly. I'll have to take that out. You will have a significant effect of factor A. I'm not sure why. So ignore that. If you don't have an interaction though, so you're going to see this in your lab handout. If you run a two-way ANOVA, you don't have to test the interaction. You can just be looking at the effect of factor A controlling for factor B, or the effect of factor B controlling for factor A, but you don't have to look at the interaction, right? If that's the case, you'll also see it in the course packet. If that's the case, then here's the table you would use, right? Notice we're just missing the row that corresponds to the interaction. That's really the only difference. I just wanted to put this in here just so you, I mean, almost always you're going to run the full model, right? You want to estimate this interaction here. But sometimes, maybe if this isn't significant, for example, you end up with a slightly more powerful test if you drop the interaction and just run the main, this is called a main effects model of just factor A, factor B, and that's it, right? Two main effects, but no interaction. So that's an ANOVA table if you do it like that, and how you compute the degrees of freedom and the mean squares and the F statistics. So you don't have to calculate these sums of squares by hand. I'm putting this out here right now because I'm about to show you lots of extra stuff, so feel free to skip it. But I want you to have an appreciation. I think it's important to have an appreciation of like what is actually going on under the hood when you do a two-way ANOVA. Like, what are we doing with these means? Where do these sums of squares come from? Again, you won't have to ever calculate these by hand. What you'll be doing is running two-way ANOVAs and interpreting the output and doing a write-up, right? But I want to show you this because I think it'll give you a much richer picture of what a two-way ANOVA is doing, and it helps you understand interactions as well. So think about it like this. Think about a table here, and I'm going to fill this in with real numbers here in a second so to make it concrete. But let's say that A1, A2, all the way up to, ever how many groups you have for this factor. Let's say this is, low dosage, middle dosage, and high dosage, right? And let's say this is like younger people, middle-aged people, and older people, or something like that, right? Just the groups for each of your two categorical variables. One categorical variable will be in the rows, and the other will be in the columns. And then you'll have individual observations. So like, what's the recovery for this person who was in the young group and got the low dose, right? They're going to be people that fall into each of these categories. if you take the average, like let's say you want to know the average, if this represents the low dose, what's the average of all people who got the low dose? You would just average across everybody, right? And this will be uh, sometimes called like a marginal mean. It's in the margin. It's just the average of the people who got the low dose, or the average of row 1. Here's the average of row 2, or the average of people who got the middle dose, right? This will be the average of row 3, or the average of people who got the high dose. What if you want to know the average recovery rate for just older people? Well, that's this one, right? Just average everybody in this column. What about for middle-aged people? Average everybody in this column, right? Average of the second column. How about this one? For young people, average the column. So these are just averages. For each of your categorical variables, right? For each group of each of your categorical variables. And here's just the overall average. So regardless of what group the people fall in, this is just the overall average recovery rate. And again, y is denoting the response variable, and a and b are just the categorical explanatory variables or factors. Cool. So there's going to be A by B cells, where A is the number of groups in factor A and B is the number of groups in factor B. So here there's 3 and 3, right? So you have data in 9 cells, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So those are your cells. And in this case, it'll be balanced. We're gonna have all the cells contain the same number of observations. Cool, so your total sample size is just the number of groups of factor A times the number of groups of factor B times the number of observations in each cell, right? Because A times B is the number of cells. If there's 9 cells, let's say there's 5 people in each group, that'd be, 9 times 5. Cool. And these are just, in case you want to review, these are just the grand mean, the mean of row I, and the mean of row J. We'll talk also about cell means if we take the average of just these people, or just these people. But that's kind of confusing, right? It's abstract. So let me make it concrete for you. Let's say we're doing an example. Let me scoot myself over. You want to see whether detergent type, so 2 different brands of detergent, brand A and brand B, or water temperature, so cold, warm, or hot, affects how clean your clothes are getting when you wash them. And let's say you have some rating of cleanliness or cleanness from 1 to 15, 15 being super clean, 1 being terrible. Let's say you wash 24 loads of laundry, and you wash 4 loads in each of the 6 conditions, right? Because there are 6 conditions. There's A and B detergents, and then there's cold, warm, and hot. So you'd say detergent A in cold, warm, and hot, and then detergent B in cold, warm, and hot. So if you do 2 times 3, you end up with 6 possibilities. A cold, A warm, A hot, B cold, B warm, B hot, right? And maybe this is the way your data turn out. Maybe detergent A, when it's cold, the 4 loads have pretty low cleanliness ratings. Maybe when detergent B is here, they're a little bit higher, but not, maybe not on average. Looks like hot though, right? If you use detergent A in hot water, the cleanness ratings are going up. If you use detergent B in hot water, the cleanness ratings look pretty high. The warm look kind of in the middle, right? So this is just your actual data. There's 24 observations, 24 loads of laundry. And you could compute, hey, what's the average cleanness for a cold load? What's the average cleanness for a warm load? What's the average cleanness for a hot load? How about for detergent A? What's the average? What's the average for detergent B? What's the overall average, right? You can just compute these by taking averages. So let's do that, right? So the average for cold is just 5. So if you wash your clothes in cold water, the average of all those loads is 5. In warm water, the average is 11. In hot water, the average is 11 and a quarter, right? For detergent B, the average is 10, which is pretty good. For detergent A, it's a little lower, right? The average is 8.16 repeating. And then your overall mean, the overall cleanliness rating, on average, if you average all these together, it's a little over 9. Cool, so we've got these averages, right? So just like, think back to one-way ANOVA, right? If you just focus on either the rows or columns at a given time, right? So maybe if we just did a one-way ANOVA looking at cold, warm, and hot, you'd be asking, hey, are these means different enough from each other, right, with respect to the noise, to suggest that cold, warm, and hot do actually affect cleanness differently, right? So you can say, hey, average for cold from the grand mean, square it, take the average of warm, the difference from the grand mean, square it, and take the average of hot, the difference from the grand mean, square it. Sum those up, and that's just your sum of squares for temperature, right, for that factor. You can do the same thing for this one. How far is detergent A's mean from the grand mean? Take that difference and square it. How far is detergent B's mean from the grand mean? Take that difference and square it. Add those up, and you have to weight by the number in each group, right? So just like last time, I mean, I'll show you the full formulas, but effectively all we're doing is computing those separate sum of squares between groups, but for each different factor. Oops. And again, right, so some of these formulas are going to look crazy. You don't have to know any of this. Just bear with me and like try to just think about it in an abstract way if you don't want to go through and plug and chug. But I want to show you where these numbers come from, right? I want you to be able to, you know, if you have a balanced design, I want you to be able to go through and compute the sum of the squares by hand if you wanted to. Because I was really, you know, it's always nice to be able to, you know, see where these numbers come from. I hate just showing you something like black box, like, oh, and it spits out the magic numbers. And it's like, wait, what are these, right? So cool. So just like before, right, the sum of squares for factor A, how far is, you know, this row mean from the overall mean? How far is this one from this one squared? How far is this one from this one squared, this one from this one squared? You have to weight them by the number in each row. The number in each row is just the number of groups of the other factor times the number in each cell, right? So that's, if there's 5 in each row times 3, that would give you 15. I'm sorry, 5 in each cell times 3 different columns, that'll give you 15 in this row, right? So 15, you know, like whatever that is. And then the sum of squares for factor B will just be how far is this one from the grand mean, how far is this one from the grand mean, how far is this one from the grand mean, square them, add them up. So those are just like doing regular ANOVA sum of squares between, right? For one-way ANOVA. The interaction sum of squares are hairy. They're annoying to calculate. I mean, just look at this thing, right? You have to do the effect of, so first you have to get the cell means. So the cell means, we have to compute what the average is in this cell, what the average is in this cell, what the average is in this cell. We have to get those. You have to subtract the effect of the row means and subtract the effect of the column means. Square that and add them all up. It's a pain. I'll show you how to do it, but it's a pain. Then the errors, right? The sum of squares error. Again, this boils down to your denominator, right? This is the variability you can't explain by knowing factor A, factor B, or the interaction, right? This is just the difference of each person's response from the cell mean. So how far is each individual's actual response from its cell mean? Do that for everybody, square them, add them up, and those are actually your residuals. So you just square the residuals and sum them. It's literally the sum of the squared residuals. That's your sum of squared error, or your within cell sum of squares if you want to think of it that way. And then finally, the sum of squares totals, just like in a one-way ANOVA. How far is each observation from the grand mean? Square them, add them all up. So here's just a way of showing cell means, right? So if you average across everybody in each cell, you just get the average for each cell. In our example, we can go ahead and average these different wash quality or cleanness ratings for each cell. So we can see, for example, that detergent A, when it's cold, it had an average cleanness rating of 5. Detergent B, when it's cold, also had an average cleanness rating of 5, right? If you average 4, 5, 6, and 5, that average is 5, right? And if you average 6, 6, 4, and 4, that average is also 5. So those are your two cell means there. Same for warm, right? Detergent A in warm water had an average of 9. That's a little lower than detergent B in warm water, average of 13, right? And so on. So you can get those cell means. And then you could go and compute the sums of squares by hand. You can also plot these cell means. So these plots are going to be huge later, but I just want to show you what happens if we plot these cell means. So imagine that we put detergent type on the x-axis. What are we going to do? Let's do it the other way. Let's put temperature on the x-axis. And then let's put detergent type on the y-axis. And let's plot these cell means. If we do that, so remember in cold A and B, they both had averages of 5 and 5. So there's 5 and 5, they're overlapping, right? For warm A and B, that's 9 and 13. So if we look here, warm, detergent A is red, detergent B is blue, there's 9 and there's 13, right? So we're just plotting those cell means. And finally for hot, what was it? 10.5 and 12, right? So for hot, we have mean wash quality of 10.5 for A. For B, we have 12. Interesting. So when you're looking at differences between detergents, you're looking at differences between those two lines. And it doesn't look like they're constant, right? So it looks like when the water's cold, they both suck equally, right? They're both like a 5 cleanness rating. When the water's warm or hot, though, it looks like detergent B is doing better, right? It gets higher scores than detergent A when the water's warm or hot. The blue line is above the red line. Interesting. So we may have a significant interaction here. The effect of detergent looks like it might depend on what water temperature you're using. In order to see if it's significant, we'd have to run the actual ANOVA and interpret it, right? But this is going to get us started thinking about interactions. Does the effect of detergent differ depending on the water type? It looks like it might, right? And this is a really small sample, right? Each of these, like this is just for illustration, like just so you can compute these by hand. You ordinarily wouldn't do something like this with only 4 observations per cell, but that's fine. It's just an example. So if we were to run this ANOVA, and again, we won't go through a full like write-up and stuff for this one. I just want to illustrate to you where these sums of squares come from. If you run this ANOVA in R, you're going to get the effect of detergent, the sum of squares, the effect of temperature, the sum of squares, right? So detergent sum of squares is like 20, temperature sum of squares is like 200, the interaction sum of squares is like 16 and a third, and then your sum of squares error, or the residual sum of squares, is like 37. If you add all those up, you get the sum of squares total. This is just to get you thinking about this, right? So we haven't talked about interpreting these things or anything yet. I just want to show you these are the correct sum of squares. Can we calculate them by hand? Yeah. So, and again, this is totally extra. This is super extra. You won't have to do this by hand ever. But just in case you wanted to, we can compute the sum of squares for detergent, right? How far is each of the detergent's averages? So detergent A had an average of 8.167, and detergent B had an average of 10. How far is that from the grand mean? Square them, add them up, make sure to weight. So there's 4 in each cell times 3 different columns. That means there's 12. So this is based on 12 things. So 12 times that gives us 20.16, 20.16, right? It's the same quantity there. Same thing for temperature here. So how far is each individual temperature mean? So this is the mean temperature for, the mean cleanness for low temperature, mean cleanness for high temperature, mean cleanness for middle temperature, mean cleanness for high temperature. How far are those from the overall mean, right? So this is just variability of the temperatures around the grand mean, or the temperature means around the grand mean. Make sure to weight it by the number in each temperature group. So there's like 8 observations in the low temperature group. There's 8 observations in the middle temperature group. There's 8 observations in the high temperature group. So just multiply that by 8. You get 200.33, 200.33, right? So compute those sums of squares. The interaction sums of squares are nastier, so I won't walk through every step of this, but you can go ahead and run this and you'll see that, in fact, you can probably just copy and paste this into R, and you'll see that it gives you 16.33, which is exactly what the interaction sums of squares are here. There's a shortcut to calculating those that I'll show you later. And again, you don't need to know this, it's just extra. But just to show you where these numbers come from. They're just, they're just sums of squares. You're literally squaring how far a mean is away from another mean, adding all that up, and then weighting it by the number in each comparison. And you can do the same thing for residual, or the error sum of squares. So anyway, totally extra. Don't sweat it if this isn't doing it for you. Totally fine. You'll never have to do it by hand. So we'll come back to this example at the end and do like a full analysis and like write-up of it. I just wanted to get you thinking about what sums of squares represent in a two-way ANOVA situation. And we've already sort of seen this idea of like, oh, maybe the effect of one variable depends on the other variable, right? Let's look at that. Let's take a bit of a deeper dive and sort of look at all the different ways a two-way ANOVA could work out. So when you run a two-way ANOVA, these are kind of the 8 different ways it could work out. Maybe nothing is significant. So maybe there's no effective factor A, no effective factor B, no interaction, right? It happens. That's life. It happens a lot. Maybe you just have a main effective factor A or a main effective factor B. Maybe you have a main effect of both factor A and factor B, but no interaction. Maybe you have a significant interaction and no main effects. So no effective factor A, no effective factor B, but there's an interaction. That one's really cool. Maybe you have an interaction with the main effect of A. Maybe you have an interaction with the main effect of B. Maybe you have an interaction and both main effects are significant. What would this look like? Like, what does this mean? How can we visualize this? I think that visually presenting these different scenarios is like really pay attention to this next bit, because this is where you'll gain a deep appreciation for interactions. We're going to take it super, super basic. No crazy math. You're just going to be looking at pictures. And you'll be able to see what a main effect is and what an interaction is in the pictures. Cool. So let's do it. Pretend, here's the scenario. You're looking at, I don't know, recovery, right? Or like recovery rate or something, some health outcome. And you've got a treatment group and a control group. So you've got some drug and you want to test it, right? You think the drug is going to improve the outcome. Then you've got adolescent participants in your study and adults, right? So you've got age. So there are 2 categorical variables here: treatment, or condition, if you will, control and treatment, and then age, adolescent or adult. What I'm plotting here, so this table right here is just showing you the cell means, and this is all made up, right? This is just, pretend these are the cell means, and then pretend these are your means for, so this would be the mean for control, right? The average outcome for control would be 3. The average outcome for treatment would be 3. The average outcome for adult would be 3. The average outcome for adolescent would be 3, right? The average outcome for adolescents in the control group would be 3. The average outcome for, and so on, right? So this is your grand mean. The overall average outcome is 3. This is what it would look like if you didn't have any interaction or main effects, right? And if you were to make a plot of this, so everything in this plot, it's going to be just like the plot we saw before. We're just plotting the cell means. So here, treatment and control. So age is indicated by the color. So red is adolescent, blue is adult, and then treatment and control, the condition is on the x-axis. The outcome is on the y-axis, right? If you were to make a plot of these cell means, well, they're all 3, right? Adolescent in the control group is 3. Adult in the control group is 3, so that's that blue dot. The red dot's underneath it, right? It's overlapping. Adult in the treatment group is 3. It's that blue dot. And then adolescent in the treatment group is 3. So you just have this flat line, right? Those cell means are all equal. Nothing interesting is going on there, right? So there's no difference in between control and treatment. So there's no effective condition. They're both 3. There's no difference in adolescent and adult. They're both 3, right? So there's no main effect. There's no main effective condition. There's no main effective age. And there's no interactions. We'll talk more about interactions in a second. You'll be able to see what they are more clearly once we actually are dealing with one. Just know that there's none here, right? The effect of being an adolescent or adult doesn't depend on what condition you're in. The effective condition doesn't depend on whether you're an adolescent or an adult. It's 3 regardless, right? So this is super boring, right? Nothing cool is going on here. How about this? What if you have a main effect of the treatment, or the main effective condition, right? If you have a main effective condition, in this case it's saying, oh, the average in the treatment group is 4, but the average in the control group is 2, right? So 4 is higher than 2. And we're assume for all these examples, don't worry about significance, right? Assume you have a sample size of 1 billion and every little tiny difference is significant. If these numbers are different, we're going to talk about it as an effect, right? So here it looks like treatment has a higher average outcome than control, right? Therefore higher than the control group. But if you look at adolescents and adults, the average outcome is 3 for adolescents and 3 for adults. So there's no main effective age. There is a main effective treatment, but there's no main effective age. We can plot this, right? So again, if we're looking at the color, so red is adolescent, blue is adult, notice that in the treatment group, both adults and adolescents in the treatment group have an outcome of 4 on average, right? So we plot both of those means there. And that's higher than both of those groups in the control group. So there's a main effective condition, but there's no difference between ages, right? These lines are perfectly overlapping. Regardless of what age you are, there's no difference in average outcome, right? Cool. There's no interaction here either, right? Because the effective, in this case, the effective condition is to raise you from 2 in the control to 4 in the treatment, right? And that's the same for adults as it is for adolescents. So when you're, regardless of if you're an adult or an adolescent, it doesn't matter. It's the same thing. In the control group, your average outcome is 2. In the treatment group, your average outcome is 4, right? Cool. Anything else about this? I think that's good. Grand mean. I mean, you can see the grand mean in this plot, right? If you took the average of all 4 dots, right? The red and the blue dot that are here and the red and the blue dot that are here, the average of 2 and 4, right? The average of the y-axis, 2 and 4, would give you 3, right? So it would be right in the middle. So the average for adults is 3. If you average the red dots, you get 3. If you average the blue dots, you get 3. And if you average all of them, you get 3, right? Cool. What if you have a main effective age? What if age is having an impact on the outcome, but treatment is not, but condition is not, right? So you could look at the means for condition, treatment and control. They're both 3. But interesting, so it looks like adolescents have a higher mean outcome than adults do, right? Regardless of the treatment. Because in the control condition, adolescents are 4, adults are 2. In the treatment condition, adolescents are 4, adults are 2, right? Cool, and you can see this. First of all, when you go from control to treatment, what happens? Nothing. It's a flat line. It's a flat line, right? So there's no effect of condition. But the red line is higher than the blue line, right? The adolescents have a higher outcome than adults do, right? So we have a main effect of age. If you're an adolescent, you have a higher outcome than adults, right? If you were to average, all of these dots, these 4 dots, you get an average of 3, right? So 4, 4, 2, and 2, average those, you get 3, right? That's the average outcome overall. And again, this is just for illustration, right? Just like thinking about cell means and plotting them and how you can see main effects and interactions. So when you're making plots like this, so far we've seen if the lines are slanted, right, you might actually have a main effect of one of your variables. If the lines are separated, like this, but not slanted, you might have a main effect of the other variable. Cool. And notice, right, there's no interaction. So regardless of whether you're an adolescent or adult, the effective treatment is nothing, right? Regardless of whether you're in treatment or control, adolescents are 4, adults are 2, right? Here's where you have 2 main effects. So what if age and condition are both impacting the outcome independently, right? There's no interaction. So if that's the case, you might end up with something like this. So the average outcome for people in the treatment group is 4. The average outcome for people in the control group is 2, right? So in the treatment group, how do we see this? If we look at this plot, in the treatment group, the average outcome is 4. So we look in the treatment group and we average the adults and the adolescents. The adults are 3, the adolescents are 5. Average of 3 and 5 is 4, right? So that'd be right there. If you average these dots, you get the average for the treatment group, and that's 4. Cool. And then the average for the control group is only 2. That's the average of 1 and 3, right? That's 2. So that's where you can kind of see those numbers there. Cool. What about age? So for age, the average for adolescents is 4. So if you average these red dots, that's the average for adolescents. So 3 and 5, the average is 4. What's the average outcome for adults? Average these blue dots. The average of 3 and 1 is 2, right? So for adolescents, their outcome is 4. For adults, their outcome is 2, right? There's a difference there. So there's a main effect of age. Adolescents have higher outcomes than adults, and there's a main effect of treatment, right? The treatment group has a higher outcome than the control group. There's no interaction, though. And how can we see that? So in this plot, the lines are parallel. They're doing the same thing, right? So think about it, like take it by age. So for adolescents, the effective treatment is to raise your score from 3 to 5 on average. So it goes up by 2. If you're an adult, the effective treatment is to raise your score from 1 to 3. So it also goes up by 2. If it goes up by the same amount, that means the effect of the treatment is the same for each age group, right? So there's no interaction. You can also see this more simply if you so take your cell means, right? And either subtract, you can do 3 minus 1 to get 2 and 5 minus 3 to get 2. If those numbers are the same, then there's no interaction. You can do it by row too. You can say 3 minus 5 is negative 2, 1 minus 3 is negative 2. They're the same number, right? So there's no interaction. Cool. It's the same effect. The effect of treatment is the same for both age groups. The effect of age is the same for both treatment groups, right? Adolescents are 2 higher than adults in the control group. Adolescents are 2 higher than adults in the treatment group. There's no difference, right? Cool, so 2 main effects. Your plot would look something like that. This is probably the coolest one ever. Here's where you have an interaction with no main effects. So what on earth is going on here? How can we see that there's no main effects? Well, what if we look at condition, right? So in the control group, the average outcome is 3. In the treatment group, the average outcome is 3. If this was your study, you'd conclude, hey, my treatment doesn't work, right? The average outcome is the same between treatment and control, if you weren't considering the possibility of an interaction. Same thing for adults and adolescents, right? You might say, adolescents had an average outcome of 3, adults had an average outcome of 3. There's no difference, right? There's no main effect of age. But that would be really missing something crucial about this, right? Is the effect of the drug or whatever, is the effect of the condition the same for each age group? Well, just take a look at it, right? So for adolescents, what's the effect of treatment? So this red line, if you're an adolescent, if you're in the control group, you're doing pretty good. You got an average outcome of 4. But if you're an adolescent in the treatment group, you're doing badly. You have an average outcome of 2, right? So the effect of treatment is to lower your outcome for adolescents, but the opposite is true for adults. If you're an adult in the control group, your outcome is pretty poor. But if you're an adult in the treatment group, it's the opposite. Your outcome gets better. So treatment is working for adults. It makes their outcomes better, but the treatment is actually hurting adolescents. Crazy, right? So that's huge. That's a big deal. Imagine if this was your drug you were developing, right? And you did your study and you didn't model the interaction. You just said, hey, I want to see if the treatment works overall and if the averages are the same for adults and adolescents. If you did that, you'd completely miss it. You'd conclude that the treatment and the control group are the same on average, because they are, right? If you don't consider adolescent or adult, if you just average these 2 dots for treatment to get the average treatment and average these 2 dots for control to get the control, they're the same, right? Average of treatment is average of this dot and this dot, so it's 3. The average of control is the average of this dot and this dot, so it's 3. So averaging over age, the treatments look the same. But if you zoom in and see, wait a minute, does the effect of treatment differ depending on age? Yeah, it really does. There's an interaction, right? Treatment helps adults, hurts adolescents. And it does so equally so that when you average over them, they look the same. That'd be huge, right? Because you may have, let's say you did your study and you said, bummer, my drug doesn't really work. Versus if you looked at the interaction, this could really be helping adults, right? But you shouldn't give it to adolescents. So maybe your drug works really well for adults, and great, now you've got a cool finding that you can, that's huge. That's a big deal. So anyway, this is a really cool situation, this sort of crossover or disordinal interaction situation. Cool, and you can see it just because the lines aren't parallel; they're totally crossing over. So in this situation, you have no main effects, right? But you have a big interaction. Here's what it would look like if you have an interaction and a main effect of treatment, but no effect of age, right? So take a look. So in the control group, the average is 2. So in the control group, if you average these 2 dots, the average is 2. In the treatment group, the average is 4. If you average 5 and 3, 5 and 3, that gives you 4. So treatment is having an effect, right? The average in treatment group is 4, average control group is 2. So there's a main effect of treatment. Age isn't having an effect overall, right? So if you're an adolescent, the average of, so average those two cell means for adolescents, so 1 and 5, the average of those two numbers is 3. And for adults, average 3 and 3, the average of those two numbers is 3, right? So regardless of if you average the blue dots or the red dots, you get 3. So there's no overall effect of age. But there is a significant interaction here, right? So notice, how does the treatment affect adults? Well, it doesn't really, right? Adults have an average outcome of 3 in the control condition, and they have an average outcome of 3 in the treatment condition, right? But what about adolescents? In the control condition, adolescents are doing very poorly, but in the treatment condition, they're doing amazing, right? So this drug is having a huge effect on adolescents, but having no effect on adults. So modeling that interaction is really important, right? Imagine you had just done the study, a one-way ANOVA, or actually just a t-test really, and found that the treatment and the control groups are different. You might say, yeah, the treatment works. But the true story is the treatment only really works for adolescents. It doesn't do anything to adults, right? So you'd be remiss to take this drug and then prescribe it to adults because it doesn't have an effect, right? The interaction lets you see for which groups the effect of the drug is actually working. I don't know if I said that right. And how can you see the interaction in the table? Just do this cell mean minus this cell mean. So 1 minus 3 is negative 2. 3 minus 5 is positive 2, right? So those are different. So you know you've got at least numerically, an interaction. You can do them by row too. 1 minus 5, negative 4. 3 minus 3, 0. Different. Same thing in this example, right? 4 minus 2 is 2. 2 minus 4 is negative 2. Different. Cool. What if you have an interaction and a main effect of age? So maybe your other, but no main effect of treatment, right? So maybe the other categorical variable is significant. So this is telling us that adolescents have an average outcome of 4, adults have an average outcome of 2, right? So how can we see that? So adolescents, if you average, regardless of what treatment they're in, so average adolescents dots, that's 5 and 3, so they have an average outcome of 4. Average the adult dots, so that's 3 and 1, so that's 2. So the average for the adolescents is 4, average for adults is 2. But it doesn't look like the treatment's working, right? It looks like you've got, in the control group on average, the average outcome is 3, right? So if you're in the control group, looks like you have an average outcome of 3. If you're in the treatment group, looks like you have an average outcome of 3. So it doesn't look like the drug is working. But what's really going on here? So there's an interaction, right? So even though it doesn't look like the treatment's working, what's really happening? Let's look at it by group. So if you look at the effect of going from control to treatment for adolescents, treatment takes them from 3 to 5, right? So they're getting better if you're an adolescent. Treatment's working, right? It's taking you from 3 up to 5 for adolescents. What about in the adult column? For adults, you have a 3 in the control group. Getting the treatment takes you down to 1. So this is crazy. This is a drug that's actively hurting adults when you give them the treatment, but it's actually, it's helping quite a bit the adolescents, right? It's a huge effect. Again, think about this situation. If you just ran a regular old ANOVA or t-test, the difference between treatment and control, you'd say there's no difference, right? And it'd be like, oh, back to the drawing board, gotta think up a new drug. But if you looked at the interaction, if you explored, hey, maybe this drug has a different effect on adolescents than it does on adults, and we just can't see it because it's being averaged over, you'd be totally right. The drug, if you give it to adolescents, it really helps. If you give it to adults, it really hurts, right? Cool. So in general, if there's an interaction, the interaction is what's important, right? It's kind of silly to talk about, I mean, I don't know. Think about it, right? If you're going to claim that that adolescents have a higher outcome than adults, that's true on average. But look, in the control group, it's not true at all. They have the same outcome on average. In the control group, adolescents and adults are both 3, right? In the control group, adolescents are 3, adults are 3. So it's not really fair to say, adolescents have a higher outcome than adults on average. It depends on the condition, right? So the interaction is what's important here. So in general, when you have an interaction, that's what's important. You can almost completely disregard the main effects, except for in a couple cases, which I'll show you a case in a second where uh, you might still be able to interpret the main effect even when there is an interaction. But right, can't you see how it's weird to be like, hey, adolescents have higher outcomes than adults, and then you look at this plot and it's like, but not in the control group, right? So the main effect is totally qualified by the interaction. The interaction tells you what's really going on, and it's telling you the effect of treatment depends on what age group. If you're an adult, treatment hurts. If you're an adolescent, treatment helps. And you wouldn't be able to see that if you weren't modeling the interaction. Cool. You can have an interaction with both main effects, right? Think about how to see these in the plot. So the main effects here, you can see that on average, the treatment is higher than the control. So how do we see this in the plot? On average, the treatment's dots, if we average those two dots, you get a 3, right? Average of 1 and 5 is a 3. That's that 3 right there. That's higher than the average of 1 and 1, which is 1, right? So there's a main effect of condition where treatment is higher on average. So the average of those two dots is higher than the average of those two dots. That's a main effect. Likewise, you can average the adolescent dots and the adult dots and see if there's a main effect of age. So for adolescents, the average outcome was 3, right? Average of 1 and 5 is 3. For adults, the average outcome is 1, right? Adults, it makes no difference. If you're in the control group or treatment group, the average outcome is 1. So adolescents are doing better than adults on average. So there are two main effects here, right? There's also an interaction. If you do 1 minus 1, that's 0. If you do 5 minus 1, that's 4. So there's definitely an interaction here. The effect of treatment differs depending on whether you're an adolescent or an adult, right? If you look at the effect of treatment for adolescents, it helps. It raises you from 1 to 5. So you go up by 4, right? That's 1 to 5. For adults, it takes you from 1 to 1. You don't go anywhere, right? So the drug doesn't help. Getting the treatment is the same as getting the control if you're an adult. So the drug does nothing. But if you're an adolescent, it really helps, right? So again, the interaction is what's important here. And that's the thing you focus on. It's oftentimes not appropriate to interpret main effects when there's an interaction. But let's look at one last example where where it is appropriate to do that. It's this example. So notice, right, there's a main effect of both. Average treatment is higher than average control. Average adolescent outcome is higher than average adult outcome. So you have main effects of condition, main effects of age. And you have an interaction, right? So 3 minus 1 is 2. 5 minus 1 is 4. So those are different. You could do it the other way too. 3 minus 5 is negative 2. 1 minus 1 is 0, right? As long as they're different, you have an interaction. So what this is saying is the effect of condition depends on the age group. It helps adolescents. It doesn't do anything to adults, right? It takes you from 1 to 1, has no effect on adults, but it helps adolescents. But in this case, it does make sense to say there is a main effect of adolescent, right? So main effect of age. Adolescents always have a higher outcome than adults do, right? So don't worry about this so much. It's just that it's now appropriate, regardless of if you're in the treatment condition or the control condition, adolescents are higher than adults. Cool. So typically you want to focus on the interaction. That's the cool thing, right? And so far we haven't run a model or do any, testing stuff. this is all about building intuition for what an interaction looks like based on a plot of the cell means, the row means, the column means, and the grand mean. And just seeing what it looks like. Cool. Back to this example. Let's go back to look at the guinea pigs one more time. So we already asked how is tooth growth influenced by vitamin C dosage, right? We found that, vitamin C has a big impact on tooth growth, right? And every group is different. But let's add another variable in the model now. Let's do a two-way ANOVA. Is it better to give them vitamin C tablets or orange juice, right? So what supplement type is better? Does that affect tooth growth? So holding the vitamin C dosage constant, is there a difference between vitamin C tablets versus having orange juice, right? If you get if you get 2 milligrams of vitamin C, does it matter if you got them in orange juice form or in tablet form? And then, does the effect of dosage depend on what supplement type is used? Maybe going from low to middle to high has a big impact if you're giving them orange juice, but it doesn't have that big of an impact if you're giving them the tablets. We can test all those things with a two-way ANOVA. Cool. So here's this same data set, right? So here's what it looks like. There's 10 in each group, right? So there's 10 who got the orange juice in the low dose, there's 10 who got the orange juice in the middle dose, and there's 10 who got the orange juice in the high dose. Same for the vitamin C tablets. There's 10, there's 10, there's 10. So there's 60 guinea pigs overall. How many guinea pigs got orange juice? 30, right? 10 and 10 and 10. How many guinea pigs got 2 milligrams? 20, right? How many got 1 milligram? 20. This is just tabling it, right? And here's all of the data in case, for whatever reason, you're having trouble getting this working. This is all the guinea pig data, all 60 of them, right? There's the first 20, there's the middle 20, and there's the last 20, in case you want to, I don't know, in case you wanted this for any reason. It's built into R, you can play with it. Cool. And treat dose as categorical, right? So make sure it's a factor variable. R will try to treat it as numeric unless you tell it to treat it as a factor. So I'm going to skip ahead and just compute these means for you just to show you, right? So looking at orange juice, the average mean tooth growth for orange juice is like 21. The average tooth growth for the vitamin C tablets is 17. So it looks like the orange juice is better, right? Orange juice gets you better or longer teeth than vitamin C. And the dosage effect is still there, right? So the average for the 0.5 milligrams is about 11. The average for the 1 milligram is about 20. Whoa. And then the average for the 2 milligrams is like 26. So that's what we did earlier when we did that ANOVA. We said, hey, are these means significantly different, right? Are the dosage means significantly different? We found that they were, right? But now we have these cell means. So if you're one of the 10 guinea pigs in the low dose condition for orange juice, the average outcome for those guinea pigs is 13 and change. Whereas if you're in the vitamin C condition, it's almost half of that, right? Interesting. And if you're in the middle dose, for orange juice, your outcome is higher, but for the tablets, your outcome is lower, right? And if you're in the high condition, oh, interesting, it doesn't look that different. Orange juice versus tablets doesn't seem to matter too much in the high dose condition. Cool. So these are just questions, like what's the mean tooth length for the guinea pigs on the 0.5 dose? That's just this one, right? Average tooth length for those guinea pigs. I usually ask these questions in class, but it doesn't make sense to ask them now, I guess. What's the average tooth length overall for every guinea pig in this study? That's like 19, right? 18.813. That's your grand mean. And then what's the average tooth length for, let's say, guinea pigs who got the orange juice and got the 2 milligram dose. So orange juice, 2 milligram dose, that's 2606, right? Cool. So these are just, making sure you're awake. If we plot these cell means, we can see what's going on, right? So for the high dose, remember it was like 26 and 26. It didn't seem to matter. But for the middle dose, the orange juice looks superior to the vitamin C tablets. And for the low dose, the orange juices look superior to the vitamin C tablets. It looks like there's an interaction here, right? And there is numerically, but we don't know if it's significant. We have to do the full two-way ANOVA test to see whether this interaction is significant, right? Because there's going to be noise. These are just means. We need to compare these differences to the error to see if we have enough evidence to reject the null hypothesis of no interaction. This is just another way to plot them, right? So if you switched around, here we have supplement on the x-axis, dose coloring the lines. Here we have dose on the x-axis and supplement coloring the lines. So remember, like orange juice is the red line. You're doing better with OJ for the low dose, better with OJ for the middle dose, about the same for the high dose, right? So maybe there's an interaction here. Maybe the effect of dose depends on what supplement type you have. So formally, right, here's where we get serious. Here's where we state all of our hypotheses. Always your first step, right? They're going to be doing 3 hypothesis tests: effective orange juice versus vitamin tablets, so effective supplement type, effective dose, and then the interaction. So there's your 3 F tests, right? So for each of those, you have a hypothesis. So you could write them. There are a bunch of ways you can write them. This is fine. You could say controlling for dose, no effective supplement type. So the average for orange juice will be equal to the average for vitamin C tablets. And the alternative is just that at least one, that they're different. Because in this case we have 2, so they're different. The effective, like there is an effective dose. For your second null hypothesis, controlling for supplement type, no effective dose, right? Which is saying the average for low dose is equal to the average for middle dose is equal to the average for high dose, controlling for supplement type. Oops, I should have said, right here I should say effective supplement type. So that should say effective supplement. This one's right, effective dose. Sorry about that. It's just the opposite, right? Like if the null hypothesis is that the supplement types are equal, the alternative hypothesis is that the means are different, right? So effective supplement type there. Cool. And then, yeah, alternative for this one is there is an effective dosage, right? So the means, at least one of those means is different from the others. And then finally, you have a null hypothesis that there's no interaction, right? The null hypothesis are always like boring, like there's no mean difference, there's no interaction. The alternative is there is an interaction, right? Cool. So test some assumptions. You can do this in a bunch of different ways. I'll just show you a few ways, right? So go ahead and fit the full model. So in R, we can say guinea pig tooth length is our response variable by a dose asterisk sup. That gives you the interaction as well, right? So fit the full model and say data equals tooth growth. That's where the data is. Cool. If you want to eyeball the normality, just make a histogram of the residuals from this model. So just do hist fit residuals. And it looks pretty normal. It looks mound-shaped, right? Looks fine. If you really want to, have hard and fast cutoffs, you can do a Shapiro-Wilk test. Just do it on the residuals, and bada bing, you can't reject the null hypothesis of normality, so you're good. For assessing homoscedasticity, right, that's the null hypothesis. Run Levine's test, it tells you you can't reject it. So cool, you're good. Everything's good. That's all you need. You don't have to do any of this, but if you wanted to, you could compute these by hand, right? So you could compute the sum of squares for supplement type, you can compute the sum of squares for dosage, and you can compute the interaction sum of squares. If you did for supplement type, you're saying, how far is the mean for orange juice from the grand mean squared? How far is the mean for vitamin C tablet from the grand mean squared? There's 30 in each condition, right? So there's 6, oh wait, hang on. No, there's 20, there's 30, right? Because so overall, right? How many guinea pigs got orange juice? 30 did. And 30 guinea pigs got the vitamin C tablets, right? So you'll just weight it by the number total. So let me think about that. Yeah, there's 10 in each cell, right? So 10 times 3 gives you 30. Cool, so 30 times those mean differences added up. You can do that. You can just grab those means, and your sum of squares for the supplement type is 205.35. That's the same as what we had before. And if you were to do a one-way ANOVA, right, just looking at supplement type, hey, 205.4, right? It's going to give you the same thing we calculated by hand. Cool. If you want to compute the sum of squares for dosage, again, totally, like you'll never have to do this. I just want to show you. You're going to take, hey, what's the average outcome for guinea pigs in, dosage low from the grand mean, from dosage middle from the grand mean, from dosage high from the grand mean. There's 20 guinea pigs in each dosage condition, right? So we have 20 for each of those dosage conditions, so we got to weight it by 20. So do 20 times that mean difference squared plus that mean difference squared plus that mean difference squared, and you end up with 2426.43. And if you run your ANOVA of just dose, is 2426.3, right? Same thing. So you get the same sum of squares if you're doing the one-way ANOVAs. Okay, so if you fit a two-way ANOVA but no interaction, right? You can do this. In fact, you'll see this in the you'll see it in your lab handout, and you'll see it in the course packet, right? This is, like sometimes you'll want to do this. It's usually almost always you want to look at the interaction. But let's say you don't. Let's say that, existing research tells you there's not going to be an interaction. You just want to look at the two main effects. You can do predict tooth length from, or see how average tooth length differs between supplement type plus dose. So don't put the asterisk or the multiplication unless you want the interaction. Just do plus and it'll leave off the interaction. Cool. So you see 205, what we calculated before, 2426, what we calculated before, so they're the same, right? The sum of squares don't change. The residuals do change though, right? So if we go back and look, if we just look at supplement type, it doesn't look like there's a significant effect of supplement type. So it doesn't look like orange juice differs from vitamin C tablets if you just do a one-way ANOVA. Because look at our error term, it's huge, right? But if we also include dose, let's control for dose, right? So dose is going to explain a lot of that error, right? And it's only going to leave this much error left over after you've accounted for supplement type and dose. Notice now, once we've controlled for dose, supplement type is significant, right? It wasn't significant on its own, but after we control for dose, supplement type is significant. Crazy, right? So we've controlled for dose, we get a significant effect of supplement type. Controlling for supplement type, we get a significant effect of dose. It's because that mean square error is smaller, right? Dose is eating up some of that error. So the error left over is smaller, which means your denominator of the F statistic is smaller. So you get a bigger F statistic and a smaller p-value. But I don't do that very often, right? You should know how to do it, but it's not, you'll almost always want to fit the interaction too. If you want to compute the interaction sum of squares, there is a shortcut. You compute the sum of squares for the cells, and then you subtract the sum of squares for factor A and the sum of squares for factor B. So you don't have to do that really crazy formula. Get the sum of squares for cells. So how far is each cell mean from the grand mean? Weight that by the number of observations in each cell, right? So 10 times each cell mean minus the grand mean squared, and add it up. Once you have the sum of squares for cells, just subtract off the sum of squares for factor A and the sum of squares for factor B. If we do that here, we can do it by hand. It doesn't take too much time. It's kind of annoying, but if you want to see that, you can compute it, and you end up with 2740 for the sum of squares cells. To get the interaction sum of squares, we just subtract the sum of squares for supplement type, which was like 205, and the sum of squares for dose, which was like 2,400 something. If we do that, we end up with the interaction sum of squares of 108.32, which is small, but it might still be significant. We have to run the ANOVA and see, right? So here's those numbers we just calculated. There's the sum of squares for supplement type, sum of squares for dose, and the interaction sum of squares, right? And yeah, the interaction is significant. Cool. Neat. So if you want to run this whole thing, this is another way to do it. You're actually explicitly writing out main effect of supplement, main effect of dose, and you're adding in the interaction. That's the same thing as if you were to take all this and just do sup asterisk dose. They give you the same output, right? The sup asterisk dose thing, factor A times factor B, is just shorthand for that. But cool, we get all the good stuff, right? And it gives you the residual, and then these that we calculated by hand. And again, you'll never have to calculate them by hand. I just wanted to show you that. So what's going on here? If you want all the means, you can get all the means like this. Don't worry about it unless you wanted to do that for some reason. But here's our table. Here's our full two-way ANOVA table for the guinea pig example, right? Sum of squares for dose, sum of squares for supplement type, interaction, error, and total, right? Here's all our degrees of freedom. So there's 3 doses minus 1 to give us 2, 2 supplement types minus 1 to give us 1. Multiply those 2 degrees of freedom to get your interaction degrees of freedom. The error is the total sample size, which is 60, minus the number of doses, which is 3, minus the number of supplement types, which is 2. So 60 minus the number of doses times the number of supplement types. So 60 minus 2 times 3, right? N minus A times B, which is 54. 60 minus 6, 54. The total is just your total sample size minus 1. get your mean square by dividing each sum of squares by its degrees of freedom. So there's your mean square for dose, mean square for supplement type, mean square for the interaction, mean square error. Take the ratio of each of your numerator mean squares, so the dose, the supplement type, the interaction, over the error to get your F statistic. So just divide each mean square by the mean square error. Cool. There's our F statistics, and those are the same ones from this ANOVA table, right? 15 point whatever, 92, 4.1, 15 point whatever, 92, 4.1, right? Same numbers. The critical values, so cutoffs for significance, will be different for each of these because they have different levels, right? So there's 2 degrees of freedom for dose, 1 degree of freedom for supplement type. So we need to get the F statistics, the critical values that correspond. So for dose, we have 3.16 as a critical value. Yeah, it's way above that, right? So we can reject that null hypothesis. The critical value for supplement type is 4.02. Our F statistic is much bigger, right? And then the critical value for the interaction is the same as this one, right? 2 numerator degrees of freedom, 54 denominator degrees of freedom. 3.16, hey, we're bigger than that, right? We can reject the null hypothesis. It's significant. Cool. So what's our decision? They're all significant, right? We have a significant interaction though, and that's what's cool. So we should really look at that interaction. But you can reject everything, right? Reject all the null hypotheses, but the interaction is what's important. We'll do a write-up in just a second, but here's the r squared, right, or eta squared. You just do 1 minus the proportion that's due to error. That gives you the proportion that isn't due to error, right? So the error sum of squares over the total is the proportion due to error, right? So 712.11 over the total sum of squares. Do 1 minus that, and you find that the total proportion of the variation that the model can explain is 79.4%, which is pretty high. And you can grab that from the model too if you're using R. Make sure you know how to do it from the sum of squares though. Cool, so here's a bit of a caveat, right? So you can do all this by hand and it's going to work totally fine when your data are balanced. So if you have equal numbers of observations in each cell. But in the real world, right? So like for your project, you're going to have different numbers of people in each cell. And that makes the sum of squares calculations a bit more complicated. To get the right calculations in R, that's why you use the type 3 sum of squares. And it'll give you this intercept thing. You can ignore that entirely. So just to show you what I mean here, you're going to always run your two-way ANOVA like this. So just like in the lab handout, you're going to use some contrasts. So you just go ahead and just run this line, then fit your model with the interaction, right? So it's got the asterisk. And then capital A ANOVA on your model fit object and say type equals 3. These are the common sums of squares that, they're pretty common in most disciplines. It's conventional to report type 3 sum of squares. And if you notice, 205, 2426, 108, those are all the same ones we calculated by hand, right? So it doesn't change anything here because our data are balanced. We have 10 guinea pigs in each condition. You won't have that luxury unless you get really lucky or you did a full factorial design. So don't worry about it. When you run two-way ANOVAs, do them like this, and you'll get the correct output every time. Make sure to run all 3 lines. Cool. And again, ignore that intercept term. It doesn't really mean anything. Just focus on the sum of squares for supplement type, sum of squares for dose, factor A and B, then the interaction sum of squares. It's the same output. Cool. Here's a full write-up. So in light of everything we did, right, we ran the full two-way ANOVA. We saw that there was an interaction. We got the R squared or the eta squared, the proportion of variation you can account for with, supplement type, dosage, and the interaction. Cool. And you could do post hoc tests. We'll talk about that in a second. You typically won't have to. You might want to on your project. Cool. So here's your write-up, right? So we did a two-way ANOVA to assess the effect of dosage of vitamin C and supplement type of vitamin C on guinea pig tooth growth. We had 2 significant main effects. So while controlling for supplement type, there was a main effect of dose, and you give your F statistic, degrees of freedom, there's the F statistic. P-value was small, right? Or you can put the critical value, whatever. And while controlling for dose, there was a significant effect of supplement type. So 2 main effects, right? this one should have a 2 while controlling for, yeah, that should be a 2. I changed the slides at the very last minute. That should be a 2 there. Don't worry about it. Because there's, right, the numerator degrees of freedom for dose, there's 3 groups. 3 minus 1 is 2. So just change that one to 2. You can see right here, 92, the degrees of freedom numerator are 2, right? So it should be 254. This one should be 154 since there are just 2 supplement types. There's that test, and the p-value is 0.0002, 0.0002, right? And then here's the cool thing, right? So hang on a minute. These are qualified by a significant interaction. And then you cite the interaction stats. The effect of dosage on tooth growth depends on which supplement type is taken, right? And so all these things together account for 79.4% of the variability in tooth growth. Cool. So again, it's telling us that the effect of dosage depends on orange juice versus vitamin C. So for example, if you get a 2 milligram dose, it doesn't do anything, right? I mean, it's going to be high overall, but there's no difference between orange juice and vitamin C. But the effect of dosage is going to, or you could think of it either way, right? The effect of supplement type depends on the dosage. So if you go from orange juice to vitamin C, orange juice is better than vitamin C in every dosage type except for the high dose. Basically, when you get to a high enough dose of vitamin C, it doesn't matter how the guinea pigs are consuming it, right? It's going to have a big impact on their tooth growth. Whereas when they're getting lower doses, it seems to be the case that orange juice results in greater tooth growth than the vitamin C tablets. And you can plot it this way or the other way or whatever, right? You could ask, hey, you know, are these means different? Are these means different? Are these means different? You can compare all your cell means if you want. Let's look at orange juice and ask, is this one different from this one? Is this one different from this one? And then let's look at vitamin C tablets and say, is this dose different from this dose? Is this dose different from this dose? So if we do that, we're saying, hey, in orange juice, if you compare, you know, low to middle, low to high, middle to high. And if you look at vitamin C, you'll compare low to middle, low to high, middle to high, right? And I'm going to go ahead and not adjust these. Let's just do Bonferroni, right? So we're doing 6 tests here. So our significance level is 0.008. So everything is still significant except for orange juice, the difference between the difference between middle and high. That's not less than, it's less than 0.05, but it's not less than our adjusted significance level of 0.0083, right? So that's saying for orange juice 1 and 2 milligrams, for orange juice 1 and 2 milligrams, those aren't significantly different. That's all that's telling you. Cool. So you can do a bunch of post hoc tests, right, if you want. You might consider that on your project, but you won't have to worry about it otherwise. Okay, so if you'd like to do some extra practice, I'd strongly encourage it. So check out the course packet, right? It's got some, like, walk through it and follow the solutions as well if you get stuck. It's especially chapter 15b, number 3. That's a great one to practice on. There's an example with no interaction, right? Just looking at the main effects, and then running one with an interaction. I've also got some additional examples in the slides. Yeah, I'll go ahead and run through them. It's already been so long. And then I'll have another full example in here with a full write-up and an example about, yeah, there's the full write-up for the laundry example. Cool. Yes, I'll just post these. I don't need to, this is just if you want extra practice, right? I definitely do the course packet stuff first, but just in case you're curious. All right, y'all. Sorry that took so long. I spent a lot of time reviewing. I hope this was useful to you. I'll fix those typos in the slides before I post them. And good luck to you. Spend time with this topic. It's a really important topic. You'll see these all over, regardless of what field of research you're involved in. So neat. I'll see y'all soon.